Now let's talk about different distributions. The first one is normal distribution. You can see there are three parameters of the normal distribution: mean, variance, and skewness. But skewness of the normal distribution is always zero. So normal distribution is basically two parameters distribution. If you know the value of mean and value of variance, you can define the distribution. So if you look at the um, equation here, you have 2 pi sigma square e to the power x minus mu divided by 2 sigma square, right? So mu and sigma are the unknown values. So if you define what is mu and what is sigma, then you can define this equation or this distribution. On the figure here, you can see the probability distribution function. So this is the probability distribution function, and this is the cumulative distribution function. This PDF figure shows different normal distributions, right? So this first one is the normal distribution with mu equals to 0, mean equals to 0, and variance of 0.2. Second one, which is red, is also has mu equals to 0, but variance of 1. And third one, this yellow one, has mu of 0 and variance of 5. The variance shows how the data is spread, right? So even though mean is same for all these three distributions, the shapes are different due to the variances, right? When the variances are different, their shapes will also be different. So we can see from this figure, when the distribution has a very high spike towards the mean, that means data is tightly packed around that mean. So for the blue one, most of the data are around their mean. Whereas this yellow line shows that the data are more or less evenly spread within this range, right? So the variance tells us how the data is spread within its range. Now, the third figure, another figure here is the green distribution, and this is also a normal distribution, but its mean is not 0. So it basically shows it is not necessary for mean to be 0. The mean can be any value. The only point is the skewness has to be 0. Okay, if the skewness is 0, then uh, it can be the normal distribution. So for a distribution to be normal, uh, skewness has to be 0, and it can be any mean value. Now, similar kind of information we can gather from the CDF also, because a normal distribution is symmetric at its mean value. Okay, let's look at this green value. So it is symmetric about -2, which means the area under this PDF, left side of -2 and right side of -2 should be equal. And we also know that the area under the probability density function has to be 1, which means the left hand side area should be 0.5 and right hand side area has to be 0.5, and same with other distributions as well. So same thing we can see from this cumulative distribution function, right? So when we go and read this 0.5, right, so it should give us what is the mean value. So 0.5, and if you go here, go to this graph and then go down, and you see the mean value is -2. So similarly for other three, we know the mean value is 0, right? So for first three, blue, red, and yellow, mean value is 0. And if you go from here and read the uh, probability, then we see this is 0.5. So cumulative probability is 0.5 at mean equals to 0. So for both green and outer distributions. Let's look at an example of how to calculate the probability using normal distribution. In the previous slide, I've shown the equation of the cumulative probability and probability density function, but there are tables also available to calculate the probabilities. And for normal distribution, using table is easy, but also obviously you can use the equation as well. So here I'll show how we can use table or how we can use Excel to find out the probabilities. So let's say we have a mean and standard deviation of the data, which is 0.5 and 0.2. So we don't know the details of the data, but we just know mean and standard deviation. And for the normal distribution, we know we need only two parameters, mean and standard deviation, right? So this is two parameters distribution, and we need mean and standard deviation. From this, what we want to find out is the probability of event being less or equal to 0.1. Okay, it may be discharge, stream flow 0.1 meter cube per second or less, right? Or it can be uh, any other variable. So we want to find out what is the probability of an event being uh, 0.1 or less if the mean and standard deviation of the uh, sample data is 0.5 and 2. So first what we need to do is we need to standardize or normalize the variable, because if we look at the river flow data, you may have 100 meter cube per second, 300 meter cube per second, 20 meter cube per second, and so on. So you can have this kind of variables. Rainfall data can be 2 millimeter, 7 millimeter, 10 millimeter, 100 millimeter, and so on. So you may have different values, right? So to use the same table for all different kind of values, first we need to normalize the data. That means the z value is x minus mean of that data divided by the standard deviation. So once you know the mean and standard deviation of data, you can calculate the z of this data. And similarly for rainfall or whatever the parameter we are looking for. Okay, for this data also we calculate x is what we want to find out, right? So for 0.1 we want to normalize that data, so x minus mu, which is mean, divided by the standard deviation, and it is 0.2 minus 0.2. So that is what we are trying to find out from the table. So if you look at this figure here, if z equals to 1.96, we can calculate the cumulative probability. So what does that mean? When z equals to 1.96, the probability or the probability of the values being 1.96 or less is the area under this curve, so the whole area under this curve. But we know the normal distribution is symmetric, so this part is 0.5, and right hand side will also be total 0.5, but up to that point is 0.470. Okay, so similarly, if the z value is 0.55, how would we read? Z is 0.5, and we go to the 0.05 here, and that is 0.2088. So cumulative probability of the value being 0.55 is 0.2088, which is up to here, so this side only, plus you need to add the left hand side, which is 0.5, right? So that's how we use this normal distribution table. Now in this problem we want to find out when z is minus 0.2, not plus. So when it is plus, we read the table and add 0.5, but when it is on this side, that means from here to here the area is 0.5, we know, but we need to deduct this part, right? How we deduct this part? Because this distribution is symmetric, at the center. So we calculate this part, okay, minus 0. To find out minus 0.2, we calculate what is plus 0.2, and then we deduct that part from 0.5. So 0.5 is total area minus this part will give us the cumulative probability up to that point. So that's what we do here. Fz equals to 0.5 minus f of 0.2. So what is f of 0.2? Is 0.0793, and that gives us 0.4207. And that is the area under this curve. Okay, so this is the area up to that point, and the probability is 0.4207. So the probability of the variable being 0.1 or less is 42.07%. And you can also use the Excel to calculate. So you use normal distance, dist normal distribution in Excel function, and you put the value of x, you put the value of mu and sigma, and if it is true, which means the cumulative, then it will give you the value of the probability. This is exponential distribution. You can see the probability density function fx equals to lambda e to the power minus lambda x, and that means you have only one parameter. So this parameter is called this distribution is called one parameter distribution because you just need one parameter, which is lambda. So probability density function is lambda e to the power minus lambda x, and you can also calculate the cumulative distribution function. And the PDF and CDF looks like this. With different lambda, you can see different kind of PDF curves, and similarly for CDF with different lambda, the values are different. Okay, and here we can calculate the mean, variance, and skewness using the lambda value. Okay, so the mean, variance, and skewness of the exponential distribution is mean equals to 1 over lambda, variance is 1 over lambda square, and skewness is always 2. Let's look at an example of exponential distribution, how we can use this exponential distribution. This is data of gauge height. The station is Fitzroy River at Rockhampton, and it shows the highest annual flood peaks. Okay, and we know 1918 flood was 10.1 meter, which is the highest. So we are looking at only the moderate floods in this example. We see the record from 1858 to 2020, and we have the data based on this information only. There are 28 moderate floods within that period, 163 years. Okay, what we are assuming is when the data are not available, they are below the moderate flood, so we just ignore that. Now the question is, what is the probability that there will be less than 2 years between these moderate floods? What is the probability that there will be less than 10 years between these floods? Okay, now we assume this flood event follows the exponential distribution. First, you need to check if it follows the exponential distribution or not. But in this example, we just assume it follows the exponential distribution. Okay. Now, once we are sure that this follows the exponential distribution, then we can use that to calculate the values and parameters that we require. So mean time between the floods, because there are 28 floods in 163 years, that means 5.82. So what does that mean is every 5.82 years there is one moderate flood. But you can see it doesn't follow exactly every 5.82, but that is the mean value, right? And for the exponential distribution parameter lambda, lambda is 1 divided by mu, which is 1 by 1.1 by 5.82, which is 0.1718 per year, right? Now we can calculate the cumulative probability. So cumulative probability equation is 1 minus e to the power minus lambda t, and 1 minus e to the power lambda is 0.1718 t, and that gives us now uh, the equation to calculate the probability for different years. So the probability that there will be less than 2 years between the moderate floods, you just put the value of t equals to 2, and it shows 29%. So the probability that there will be less than 2 years between the moderate floods is 29%. What about 10 years? The probability that there will be less than 10 years between the moderate floods is 82%. Okay, so there is 82% chance that there will be uh, less than 10 years between the moderate floods. We can also use the Excel function to calculate the same. Uh, you just need to provide the values. What is the value of x, okay, number of years, and lambda, and if it is cumulative or not, and you will get the same answer. So if the parameter lambda is 1.5, it's different lambda, and probability is 0.5, find given x. So what is the x? So that is the other way around of this question. You know lambda, you know the probability, but what is the that x value we are trying to find out? So we can fx equals 1 minus e to the power minus lambda x, and you can solve that for. Now, some of the distributions like exponential distribution, we don't use table because we don't need to, because the cumulative probability equation is quite easy to solve for, right? So we have this integration of the probability, and we just inserting the value we can calculate. But for other distributions where the cumulative probability function is a bit complex, we use the tables. Log normal distribution is one of the widely used distribution in hydrology. The concept of log normal and normal distribution is the same. So actually, log normal distribution is the normal distribution of log transfer data. So there is nothing else. This is only the normal distribution of the log transfer data. So what does that log transfer data means? So you have like, let's say rainfall data of 100 years. So 10 millimeter, 20, 70, 80, whatever millimeter of data. Then what we do, we first take log of the data. So log 10, log 30, log 70, whatever the rainfall is, we transfer that data in log, and then we assume that the log transfer data now follows the normal distribution. So once you convert in log, then you just assume that data follows the normal distribution, and you just use that, okay? And that is the log normal distribution. But if you have only the mean and standard deviation of the data, but you don't have whole data, or you don't want to use the whole data, but just use the mean and standard deviation of the data, you can calculate the mean and standard deviation of the log transfer data directly. Okay, so you don't need the entire set of data. Let's say you have the mean of normal data is 100, and standard deviation of the 100 the normal data is 200. Then you can use that those two data to convert to calculate the log mean and log standard deviation. Okay, and the equation is here. Mu x equals to mu x is the normal, and y is the log transferred. Okay, so mu x equals to e mu y sigma y square over 2, and sigma x square equals to this equation, or you can rearrange to find out sigma y and mu y. Okay, so if you know mu and sigma of the normal data, you can calculate mu and sigma of log transport data. Log normal distribution, also you can use Excel spreadsheet to calculate the values. So for given x value, the probability is given by this log normal dot distribution function. And what you need to do, you need to provide x, sigma y, sigma mu y, sigma y, and the cumulative is true. Okay, so first you need to calculate the mean and sigma of log transport data, and then you can calculate the log normal distribution probability. So this is just an example uh, for given value of x. uh, Sorry, you can also calculate the inverse of log, and this function is not available for all distributions. The inverse value, that means if you know the probability, what is the value? Okay, so first one, if you know the event, what is the probability of the event being x less or equal to 10, then you just use log normal dot dist in Excel, and 10 is the value, and mu y and sigma y values and true, and you get 0.0406. But instead of that, if you know the probability, what is the if the probability is 0.406, what is the value of the event? Okay, what is the flood or what is the rainfall, and so on, for that particular probability. If you want to find out, you can use the log normal information probability, this mean and sigma, and then you can get that particular value. Now another distribution, which is also very highly used in hydrology, is generalized extreme value distribution. And you can see the cumulative distribution of this generalized extreme value, fx equals to e to the power minus 1 minus 1 c x a and b. And you can see here you have the uh, parameters a, b, and c, right? And you also need mu, sigma, and z to find those parameters. So first you need to have the mu, sigma, and the skew coefficient of your data, and from there you can calculate what are the values of a, b, and c. And once you know the values of a, b, and c, you can use this cumulative distribution function to calculate the cumulative probability. Generalized extreme value distribution is one of the highly used distribution in hydrology, and it is called generalized extreme value because with the different parameters of C, you can get a different distribution. When C equals to 0, then it becomes extreme value type 1 distribution or Gumbel distribution. When C is less than 0, it becomes type 2 distribution, and when C is greater than 0, it becomes extreme value type 3 distribution, which is also Weevil's distribution. Okay, so what are type 1, type 2, and type 3? Also in the next slide. And in this distribution, we need three parameters, a, b, and c, and they are called location parameter, scale parameter, and shape parameters. Now, what is extreme value distribution? So we know if you have like the rainfall of last 30 years, you know most of the values will be around this area, right? So at the mean, towards the mean. So uh, if you look at the 30 years time, 365 days, most of the values will be around this area. And there are very few values at the extreme low side and extreme higher side, right? But in hydrology, we are interested in the extreme side. So what is the extreme rainfall, extreme annual rainfall, what is the extreme annual stream flow, what is the those extreme are the ones that we are more interested in, right? So these extreme values also follows some kind of distribution, right? So not whole 330 years time 365 years of days of data, but only one data per year, for example. So we'll have 30 data which which will nearly fall around this area. It's not necessarily here, but most of them will be in these outlying area, right? And we want to see what is the distribution those extreme values follow, right? And yeah, and this extreme value distribution can be type 1 distribution, type 2 distribution, and type 3 distribution. They may follow other distributions, but also we can use these distributions, sorry, we can use extreme value distributions to see if they follow this distribution. When we use type 1 distribution, when the parent distribution is unbounded in the direction of desired extreme and all the moments of distribution exist. Okay, so for example, maximum flow, there is no bound towards the maximum flow, right? The flow can be any value, there is no limitation at a stream. It can be only 30 meter cube per second, and it can never go above that. We can't say that. So there is no upper bound, and in those situations we use extreme value type 1. Similarly, with maximum rainfall, we use this extreme value type 1 distribution. Type 2 distribution is used when the parent distribution is unbounded in the direction of desired extreme. And the parent distribution means when we include everything, we include all data, okay? The parent distribution is unbounded in the direction of the desired extreme, um, and all the moments, sorry, uh, but all the moments of distribution do not exist. Okay, so some of the moments do not exist. So that is that is the time we use a type 2 distribution, but not used in hydrology. And type 3 distribution is the parent distribution is bound in the direction of the desired extreme. Like for example, rainfall, the minimum rainfall, they are bounded like zero. Zero is the lower bound, right? You cannot have less than zero. So that is the lower extreme, and it has bound. And in those situations, we use type 3 distribution. Now let's see how we can use the generalized extreme value distribution. We have mean, standard deviation, and skewness of the data. We have certain years of data, and we calculate mean, standard deviation, and skewness of the precipitation data are these values. Okay, now we want to calculate uh, the parameters of the distribution and annual maximum rain of 100 years of return period using this distribution. So we have mean, standard deviation, and skewness. We assume that the data follows the generalized extreme value distribution. Now we want to find out what is the 100 years of flood, okay, sorry, rainfall. So first we calculate the parameters of GEV, which are A, B, and C, right? We have mu, sigma, and G, but we need to find out A, B, and C from this equation. And in this equation, you can see there is a the notation here, which is called the gamma function, okay? Gamma function, gamma of 1 plus C. So to solve this, first you need to calculate the C value, and you calculate the B, and finally A value. Okay. So how we calculate C value? You have the skewness, and you have the on the right hand side you have the variable, which is C. Okay. So there is only one variable on the right hand side. So if you can find the C value, you can find G, or the other way around. Now, this equation is a bit complex to solve explicitly, so I solve it implicitly, which means I first assume some random C value. Okay, so C value, you just assume some random value, and then you calculate what is 1 plus 3c, 1 plus c, 1 plus 2c, these values, gamma of those values, and then you calculate what is the denominator and what is the numerator, and finally what is the g value. So okay, for the assumed c, I calculate what is the g value, and if you compare with this actual skewness value. If not, you just change the value of c, or you just can use excel function um, to optimize that value. So this way I calculate the value of value of c, and once I calculate value of c, calculating c, b and a are not that difficult, because you can explicitly calculate those values. Okay, so then I calculate b value, I calculate a value. So these are the three parameters. So I calculate c, b, and a values of this distribution. Now, the generalized extreme value distribution is fx equals to e minus 1. You have this equation, right? And you substitute the values of c, a, and b, and you get that equation. Now, to calculate the annual maximum rain of 100 years return period means we want to find out the rainfall which may exceed the 100-year return period, right? So what we need to do is we need to find out the cumulative probability. So because this gives the cumulative probability, what we are looking for extends probability. So fx equals to e, so you just substitute the values, and you get uh, the probability. And for the given return period t equals to 100, the cumulative probability is 1 minus 1 by t, which is 0.99, right? And you substitute 0.99 here, and you get 435 millimeter of the rainfall. Okay, so if the mean is 289, and standard deviation is 459, skew is 0.17 of the given data, and if that data follows the generalized extreme value distribution, then we calculate the 100-year extends rainfall, which is 435. We want to know what is the probability distribution of our observed data, right? Does this data follows normal distribution or log normal distribution, or the Gumbel distribution, extreme value type 1 distribution? Which distribution our data follows? Because we should be sure that our data follows that particular distribution, because that is the very first thing we need to do. Once we fit our data to a theoretical distribution, and if it fits, then only we can extrapolate. Otherwise, the extrapolated data will be not accurate. So how we can check if our distribution, if our data follows a particular distribution? So there are two ways of doing that. One is to do the check with the graphical method. That means we plot our distribution, and we also plot the theoretical distribution, and we see, okay, if they are matching or not. The other method is the statistical method. In the first method, that is the graphical method, what we do, we rank the data. We rank the data. If you have like n number of observation, we rank the data from 1, and 1 is assigned to the observation with the largest magnitude. So we put the data from highest to lowest, and highest will be 1, second highest will be 2, third highest will be 3, and up to n, right? So if there are 30 data, then n will be 30. And then we calculate the probability is m divided by n plus 1. Okay, so first data will be 1 divided by 30 plus 1. Number 2 will be 2 divided by 30 plus 1, 3 divided by 30 plus 1, and so on. So that is the Weebl's formula to assign the probability for each observed data, and then we plot. But there are other formulas as well. For example, Gringotten formula, instead of using m, it gives us m minus a divided by n plus 1 minus 2a, and the a values are different. And these are not the only two, but there are so many other different empirical formulas as well. Okay, but Weibel's formula is one of the widely used method.